The emphasis of this lecture is on heat. In earlier lectures, we have addressed work as a product of generalized force, which are intensive, and extensive generalized displacement. We have also elaborated on how we can envision reversible transformation, especially in the context of work. All these things are leading towards the first law of thermodynamics. This is the mathematical expression. We have completed these parts in earlier lectures. The focus here is on heat. Both heat and work are energy in transit, thermal energy in transit for a particular system. Okay, so you cannot talk about work of a system or a heat of a system. Only when there is a transformation from one thermodynamic state to another thermodynamic state, we can talk about work interaction and heat interaction for a system. So how do we define heat? So heat is a form of energy transfer that depends upon temperature difference. Whenever there is a temperature difference and the system is not constrained to be insulated, okay, there's a possibility of energy transfer between the system and the surrounding, and if there is a temperature difference between the system and the surrounding, then there is heat transfer. In this case, for example, when the room temperature is 25 degrees centigrade and the temperature inside the soda is 25 degrees centigrade, there's no heat transfer, all right? So the heat transfer is not because this soda can is well insulated, like in a thermos, okay? That's not the reason. The reason for no heat transfer is because the temperature of the room, which is the surrounding, and the temperature of the system, this is the soda and soda can, that is 25 degrees centigrade. As soon as there is a temperature difference, there is a heat transfer. For in this case, the temperature difference is less, the heat transfer rate, that is 8 joules per second, that is less. When the temperature difference is more between the surrounding 25 degrees centigrade room air and the soda can, the heat transfer is more, right? So in all these cases, the soda can allows for heat transfer, okay? So it's not thermally insulated. We look at this constraint a bit in a slide or two. So it's also important to understand, in this case, when there is heat transfer, the soda can will, temperature of the soda can will increase and asymptotically reach the temperature of the room, all right? But it's not necessary that heat transfer needs to be accompanied by a temperature increase, okay, or a temperature decrease. So that is because you can also always consider heat transfer contributing to latent heat changes, right? So when there is melting of ice to water, even though you supply heat, there's no change in temperature. The thermal energy goes towards breaking the bonds of ice to form water at the same temperature. Okay, so heat transfer need not be accompanied by temperature change. So what exactly we mean by thermal energy and heat? There are some nuances in definition which you have to be clear. Okay, so for example, it's this is a potato. So there is the system boundary and there's the surrounding environment. All right. So we talk about the thermal energy of potato, and that is with reference to its temperature. We can talk about that, and this is the thermal energy, internal energy. These are all state functions. Okay, so and this thermal energy can be transferred to the surrounding air. Okay, because this is at a higher temperature, it can be transferred to surrounding air. Okay, so when this transfer occurs, during this transfer at the system boundary, the boundary between the system and the surrounding, that transfer, during that transfer, we refer to the thermal energy interaction with between the system and the surrounding as heat. All right, so that's what is being referred to as heat. Okay, so we can define thermal energy of a particular system. Especially, we can refer to the temperature of the system, and we can talk about thermal energy possessed by the system. But during thermal energy transfer, okay, driven by temperature difference, that interaction between the at the system boundary is referred to as heat. So there is a particular constraint called adiabatic constraint. Okay, so you have to be clear. This adiabatic comes in many sciences. Okay, so there is something called adiabatic transformation in quantum mechanics also, but here we are talking about adiabatic wall, okay, in thermodynamics. So what we mean by adiabatic wall is a wall that is perfectly insulated. Okay, there cannot be heat transfer between the system and the surrounding, even though there is a temperature difference. Okay, so you can think about many systems that approach this adiabatic wall. Okay, when you have a thermos flask. Okay, so that has a well insulated wall. You can have wood and things like that. There are many material systems which approach a perfect insulator. So this constraint is called adiabatic. Okay, so it can be broken into three word roots. It's opposite of diathermal. This diathermal means which allows for heat transfer. A, whenever you say A, you add in front, that's opposite. Okay, it's an antonym. And then these are means through or allows passing through. Okay, so adiabatic is an important constraint. Okay, so you have to understand this one extreme. All right, so where even though there's a temperature difference, there cannot be any heat transfer. However, it's also important to know that even without heat transfer, for example, in this case, with for an adiabatic system, temperature can change. How do you think? That is because of you can allow for work transfer. Okay, so that depends. That's another constraint on the system, right? There are many kinds of work transfer you can envision, which would help you increase the temperature. For example, in Joule's experiment, the system was covered by an adiabatic wall, right? But there was other kinds of work interaction that resulted in the increase in temperature of the system. Okay, so that can also be thought through. So there are three modes of heat transfer. Heat transfer is extremely important in the context of understanding, modeling, controlling climate change, greenhouse effect, and so on. Okay, so the three modes of heat transfer, amongst the three modes, the first is what we're illustrating here is radiation. The quintessential feature of radiation is that there can be thermal energy transfer without a material medium. For example, here there is sun, which is at a very high temperature. It radiates at an energy, and that gets transferred through space. When you say empty space, empty in the sense that there's no material medium, but it can sustain electromagnetic field, right? Photon fields and so on. So that radiation can get transferred, again because of difference in temperature. So, and then when it passes through the atmosphere, while it passes through atmosphere, two processes can occur. Okay, there can be absorption by molecules of the atmosphere. So there are some molecules which absorb better. Okay, carbon dioxide. Okay, so it's a greenhouse gas because it can absorb a lot of radiation, and it goes into the vibrational degrees of freedom and the translation degrees of freedom of carbon dioxide, methane gas. It's even water vapor. Okay, these are all strong greenhouse gases. Okay, and then they can absorb and re-emit electromagnetic radiation. Okay, so there is some incoming radiation, and there is a radiation that goes out. All right, and so when it reaches in this region, let's say it has reached the Earth's surface, there can be conduction of the thermal energy transfer by conduction. Okay, so that is most often important in solids. We'll see why it is so. And then there can be a third mode called convection. This is most often important in fluids. Okay, for example, when you say there is wind, okay, there is heat transfer is better when heat transfer is greater when wind is flowing. Okay, so when there is that form of heat transfer is called convection. We'll elaborate this in the next few slides, these three modes. So what is conduction? Okay, so supposing you have you are inside this winter, let's say, and there is heater inside your house. Okay, so and the inside temperature, the temperature inside the house is higher than the temperature outside. Okay, let's say imagine winter. All right, so there is some thermal energy transfer that occurs, and that thermal energy transfer occurs because the inside temperature is greater than the outside temperature. So what exactly do we mean by conduction? Okay, so if you, let's go into this particular example. So supposing there is a metal rod, this side of the rod is heated. Okay, so this is at a higher temperature. Whenever you say higher temperature, what exactly do we mean? We have taken some time to interpret this. So when this rod is at this side of the rod is at a higher temperature, this is vibrating to a greater extent. Okay, so solid. In solid, the atoms are fixed to a particular equilibrium position. The average position is fixed, but they can vibrate around the mean position. All right. So whenever you say this is at a higher temperature, the amplitude of vibration is greater. And when this is at a colder temperature, the amplitude of vibration is lesser. So when you say there is heat transfer by conduction, what is occurring? This is vibrating because it is at higher temperature, the vibration amplitude is greater. And because of this vibration, this is jiggling, making this atom jiggle, okay, the vibrate. So this is, which is making this atom vibrate and so on, okay. So this vibrational thermal energy is transferred from regions of higher temperature to regions of lower temperature. Okay, so all right, this is what exactly we mean by conduction. And as you can see, this will be very effective in solids because the vibration of one atom can most easily felt by the other atom in a solid. Okay, because it's a rigid lattice. Okay, so this might not be very effective in case of gases because these are not, first there's no vibration, even the collision between one gas molecule to other gas molecule is not as effective in transfer of thermal energy compared to what it can be in a solid or in a condensed medium. Okay, it can also be important in liquids. For example, there are in atomic energy plants, nuclear energy plants, there are liquid metals, molten metals, which are used as heat transfer medium. There also conduction can be important. At least the conduction is most effective in certain solids. Interestingly, diamond. Okay, so it's extremely effective in terms of heat transfer by conduction. Okay, so why this is counterintuitive? Diamond is a electrical insulator, but it's an exceptionally good thermal. It's exceptionally good for heat transfer by conduction. Okay, so in many glass cutting tools and so on, you use artificial diamonds because it enables facile transfer of heat by conduction. So there is a law which is which mathematically tells you about the time rate of thermal energy transfer, which is called Fourier's law. So as I said, any thermal energy heat transfer is because of a temperature differential. In this case, the temperature differential is T2, which is less than T1. So therefore, this T2 minus T1 will be a negative number. That's what you mean by less than 0. And that is inversely proportional to L. If L is very large, the conduction will be less. Okay. And it will also, you can think that if this conduction will be better if the this cross-sectional area, okay, is greater, right? So all these things are encapsulated in Fourier's law. So time rate of thermal energy transfer via conduction, that is this quantity, is inversely proportional to length, directly proportional to area, directly proportional to this temperature differential. So just because this is negative, you're having a negative sign here because this is a positive quantity. And this is a material quantity. Okay, so this is the thermal conductivity. So that depends upon material to material. For a metal, it's very high. For an insulator like wood, it's very less, right? So typically, you want to have, especially in Western places, okay, so Western countries where there's a lot of heating done in winter and cooling done in summer, you want to have very well insulated buildings. Okay, so you typically have well insulated buildings. Cement is not a good insulator, and also cement has other disadvantage. So, but overall, this is a material property that can be controlled. Okay, so well designed in terms buildings in terms of heat transfer tend to control this part. So this can be represented in a differential form in this manner. Okay, so this is a very important equation, heat transfer, for example. And there are lots of mathematical methods that have been developed to solve this equation. Right. So next we move on to the second mode of heat transfer called convection. So again, this is also very important. So with the computing speed increase has been increasing over the last many decades. Alongside with this increase is the heat generated in electronic systems. Okay, so this heat generated has to be transferred to the environment, or else it will lead to overheating of electronic components. So in older laptops, you could perceptible sound. Okay, there's a fan which kicks in when the temperature increases beyond a particular extent. Okay, this mode of heat transfer is called convection. So here this is at a high temperature, and the bulk is at a lower temperature because of the temperature differential, and because of this flow of a fluid. Okay, in this case air, there can be heat transfer from this electronic component to the surrounding environment. So it's a combined effect of conduction at the solid, because the heat till this point gets conducted, and even at this boundary. Okay, so at the boundary, the velocity of the fluid is at 0, so that heat transfer occurs by conduction. And then there is also a bulk flow, okay, which contributes to convection. Okay, it's a combined effect. So the mathematical expression for convection is encapsulated in what is called Newton's law of cooling. So depends upon the difference between maybe there's a negative sign missing here. So it depends upon the temperature difference between the bulk, and this particular temperature. Okay, so here, so TB is the temperature of this electronic component. TF is the bulk temperature of the environment. Okay, so this is a positive number. This again depends upon the cross-sectional area. This is called the heat transfer coefficient. Okay, so for convection. So to get some idea of the numbers, as engineering students, it's important to have a feel for numbers. So there are two kinds of convection. One is called free convection. Supposing there is no forced flow of air. Okay, so you just allow this component is exposed to air. Due to certain natural buoyancy effect, there can be free convection. Okay, So the heat transfer due to free convection is less compared to heat transfer because of forced convection. That's why you have a fan. Okay, when a fan pushes the air mass, that's called forced convection. Without this forced flow, it is called free convection. The heat transfer due to free convection is less than the heat transfer due to forced convection. In addition, you can see that heat transfer in gases, okay, whether it's free convection or forced convection, convective heat transfer in gases is always less effective than convective heat transfer in liquids. Okay, especially because this conduction is involved. Okay, so the conduction is better in liquids. Therefore, these two features have to be observed. There is forced convection is a better form of convective heat transfer compared to free convection, and liquid heat transfer coefficient is greater than what it is in gases. So there is this third mode of heat transfer called radiation. As I said, radiation can occur even without a material medium. So here, this is at a higher temperature, and this medium is characterized by certain quantities called emissivity. Okay, so we'll elaborate this slightly in the next minute. So this heat transfer from here to this is the surrounding medium, and this is at a lower temperature, this is at a higher temperature. This medium is at a higher temperature. But in between this medium and this medium, there's no material medium. Okay, so it is just the electromagnetic field that enables radiative heat transfer from this material medium to this material medium. So one kind of radiative heat transfer you might have already heard in your high school called the black body radiation. Okay, so this is solar radiation because sun is present at 5000 Kelvin, right? So this radiative heat transfer is very important when we address solar energy conversion, climate change, and global warming. Okay, so you have to be, it's a very, very important topic of very current interest. So you addressed this in one of your assignment. So the thermal energy distribution in across various frequencies. Okay, so it is elaborated by Planck's distribution law. Okay, so this is the equivalent of Maxwell-Boltzmann distribution law, which you might have seen in your high school. Okay, so this is very important. All these radiative Planck radiative heat transfer and Planck's distribution law played an important role in early days of quantum mechanics. Okay, so Einstein was trying to understand some results of Planck, and it helped in formulating the laws of quantum mechanics. The most fundamental theory of radiation is what is called elaborated in quantum electrodynamics. Okay, so but this is too complicated for engineering applications. So for engineering application, the law which we use is what is called Stefan-Boltzmann law. So this is the Stefan-Boltzmann constant. This is called the emissivity. For a black body, emissivity is 1. You can also, there is something called a gray body and so on. Okay, so all these things are of current interest. How to model the emissivity of, let's say, snow, okay, or a green cover. Okay, so when you plant trees, how does it change radiative properties of the system and so on? Okay, so all these things are very important topics and to understand climate change, global warming, and so on. So this radiative heat transfer depends upon this temperature to the 4th power. Okay, so this is very important to notice that. So the importance of radiation increases dramatically as the temperature increases, because this term goes as the 4th power. All right, so that's why radiation might not be very important at low temperature, but as the temperature increases, the importance of radiation increases significantly. All right. So with that, we have completed all the three modes of heat transfer. In analogy with work transfer, we can think about quasi-static flow of heat. Okay, so what exactly do we mean? So in effect, we're in quasi-static heat flow. We are talking about infinitesimal heat flow under infinitesimal driving forces. Okay, here the driving force is temperature difference. If you keep the temperature difference very, very small, the time rate of heat transfer is also very small. Okay, that's what we mean by infinitesimal heat flow. So how is this accomplished? To accomplish this, we think in terms of heat reservoirs. These are thermal energy baths of infinite heat capacity. Okay, for example, if I take a very hot temperature rod and dip it in ocean, okay, let's say sea. Okay, so the sea is imagined as a near infinite thermal bath with infinite heat capacity. Okay, so even though the steel can be at a very high temperature, when I dunk it in ocean, the temperature of ocean doesn't change at all. Okay, almost there's a very marginal, almost there's no temperature rise, even though the temperature of steel quickly reaches that of the ocean. Okay, another heat reservoir is the surrounding air, right? So your body temperature might be very high, okay, for when you have fever, for example, high, okay, but the atmospheric temperature doesn't really change because of heat generation in localized places. Okay, so ocean, atmosphere, these are all considered as heat reservoirs. Okay, so why are we talking about this? Typically, to envision a quasi-static heat flow, a system at temperature, a particular temperature, is brought in contact with a heat reservoir that has a very small temperature difference compared to the system you're considering. For example, if you want to remove thermal energy by heat transfer from the system, you bring in a heat reservoir which is at a small temperature less than that of your system. Okay, so your system temperature is, let's say, decreasing. So you do a thought experiment where different thermal reservoirs at different temperatures is brought in contact with your system. Okay, same thing. If similar thing can be thought when you want to increase the temperature of the system. You bring in thermal reservoirs, heat reservoirs that are at a slightly higher temperature to your system temperature, and then you transfer heat from the thermal reservoir to your system. So as the system temperature is increased, you envision different thermal reservoirs are brought into contact. Okay, this is a thought experiment. Okay, this is impractical. Okay, to envision thermal heat reservoirs at different temperature, but that's a thought experiment that has certain utility. So quasi-static, there are two components. One is its infinitesimal heat transfer, and then there is a reversibility. What do I mean by that? So, for example, if I'm removing heat from the system to the reservoir, because the reservoir is at a very small, when the difference between the system and the reservoir is very less, with the system temperature being higher. If I increase the thermal energy, the temperature of the heat reservoir to be slightly more, then I can reverse the direction of heat flow. Okay, so not only the heat transfer is infinitesimal, it is also can be easily reversed. Okay, so both these things go into quasi-static. Okay, so heat flow. So this is important essentially to keep the system thermodynamic properties. Okay, the thermodynamic properties of the system can be kept uniform. Okay, so when there is heat transfer, we want for when we are thinking about quasi-static heat transfer, what we are imagining is that supposing steel is getting cooled in a quasi-static manner. So there can be steel which is closer to parts of steel that is closer to the surrounding temperature. But in a quasi-static heat transfer, the entire steel, the steel that is closer to the environment, but steel that is further away from the environment, the temperature of the entire steel medium is the same. Okay, there's no there's a uniformity in temperature as the steel is cooling down. Okay, so this kind of uniformity in thermodynamic properties is achieved by this quasi-static heat transfer. It is not so important when we are talking about the first law of thermodynamics, but it is much more important when we talk about second law of thermodynamics. Okay, so in the first law of thermodynamics, see, in the zeroth law, we define temperature. In the first law, the central player, okay, is the internal energy. The central player in the second law of thermodynamics is called entropy. Okay? So to define entropy, to quantify entropy, we are going to be talking about reversible quasi-static heat transfer. In that case, it is much, much more important than what it is in the first law. So with this, we have completed our introduction to heat transfer, heat flow. Thank you.